welcome to this problem walkthrough. Today, we'll be solving problem number 1089, titled Duplicate Zeros. In this challenge, we'll explore how to manipulate arrays effectively to duplicate zeros in place while maintaining the structure of the array. Let's dive into the problem and understand how to approach it step by step. In this problem, we are tasked with duplicating each occurrence of the number 0 in a fixed-length integer array. When a 0 is duplicated, all subsequent elements in the array are shifted to the right to make space. Importantly, this has to be done in place, meaning we modify the input array directly without creating or returning a new one. Because the array has a fixed length, if any elements are shifted beyond the bounds of the array, they are simply dropped. The input array, denoted as ARR, has a length n, which falls between 1 and 10,000. Each element in the array is a single digit between 0 and 9. The function does not return anything, instead, it modifies the array directly to reflect the changes. This means we need to carefully handle the shifting and duplication without using extra space. Let's look at an example to understand the problem better. Suppose the input array is 1, 0, 2, 3, 0, 4, 5, 0. The first 0, located at index 1, is duplicated, causing the elements 2, 3, 0, 4, 5, 0 to shift one position to the right. This results in the intermediate array 1, 0, 0, 2, 3, 0, 4, 5. Next, the 0 at index 4 is duplicated, shifting 4, 5, 0 further to the right. The array then becomes 1, 0, 0, 2, 3, 0, 0, 4. Finally, the 0 at index 6 cannot be fully duplicated because the array length is fixed at 8, meaning the last 0 is truncated. The final output is 1, 0, 0, 2, 3, 0, 0, 4. This demonstrates how duplications and shifts work within the constraints of the fixed-length array. Now, consider another example. If the input array is 1, 2, 3, there are no zeros to duplicate. As a result, the array remains unchanged, and the output is simply 1, 2, 3. For a different scenario, let's examine an array made entirely of zeros, like 0, 0, 0, 0, 0, 0, 0. Here, every 0 is duplicated, but because the array length is fixed, only the first few duplications fit within the array. The output remains 0, 0, 0, 0, 0, 0, 0. These examples highlight how the presence and position of zeros affect the outcome while adhering to the fixed length of the array. To summarize the constraints and edge cases, the array length, denoted as n, lies between 1 and 10,000. Each element is a digit between 0 and 9. The operations must be performed in place, meaning no additional space can be used, apart from the input array itself. If elements are shifted beyond the array's fixed length, they are simply ignored. Key edge cases to consider include arrays without any zeros, which remain unchanged, arrays consisting only of zeros, where only the first n duplicated zeros fit, and arrays with trailing zeros, as these may not be fully duplicated. Additionally, single-element arrays, like 0 or 1, require special attention to ensure boundary conditions are handled correctly. To approach the problem of duplicating zeros in an array, one initial idea is the brute force method. This relies on iterating through the array and handling each 0 as it appears. When a 0 is encountered, the subsequent elements are shifted one position to the right to make room for the duplicate 0. The duplicate 0 is then inserted at the current position, and the process continues for the remaining elements. While this approach is simple to understand and implement, it requires shifting elements for every 0 encountered. This repeated shifting leads to a time complexity of n squared, since in the worst case, we may shift up to n elements for every 0. On the positive side, it uses no additional memory, so the space complexity remains 1. However, this inefficiency makes it impractical for large arrays and prompts us to consider more optimized solutions. A more efficient solution is the optimized two-pass approach, which leverages the insight that multiple element shifts can be avoided. Instead of handling zeros as they appear, we first calculate how many zeros can actually fit within the bounds of the array after duplication. Once we know this, the array can be processed in reverse to fill in the modified values directly. This avoids the risk of overwriting elements prematurely. The process begins by counting the total number of zeros that can be duplicated, factoring in the array size. With this information, a two-pointer technique is employed to traverse the array backward. As we move from the end of the array, elements are either copied or zeros are duplicated as needed. This strategy reduces the overall time complexity to O(n), since the array is traversed only twice, and it maintains a space complexity of O(1). While slightly more complex than the brute force method, the reverse traversal ensures greater efficiency, making it a significant improvement. The chosen solution for this problem is the optimized two-pass approach. By reducing the time complexity to O(n) and avoiding unnecessary shifting operations, it provides a more scalable and efficient solution. The critical realization here is that working in reverse allows us to handle zero duplication without overwriting existing elements, which balances performance with simplicity. This makes the method robust and adaptable to arrays of any size. On the other hand, the brute force approach was ruled out due to its quadratic time complexity, which becomes infeasible as the input size increases. In contrast, the optimized approach adheres to the problem's in-place modification constraints while delivering linear time complexity. Ultimately, it is the most effective solution for achieving the desired result efficiently, without sacrificing clarity or space efficiency. In this problem, we are tasked with modifying an array of integers by duplicating every zero, all while keeping the array's original length intact. When a zero is duplicated, the last element of the array is truncated to ensure the size remains unchanged. To tackle this, we can consider a brute force approach. The intuition here is straightforward. As we traverse the array, each time we encounter a zero, we duplicate it by shifting all subsequent elements to the right. This ensures the zero is effectively duplicated, but it comes at the cost of repeated shifting operations for every zero encountered. This makes the brute force approach computationally expensive and inefficient for larger arrays due to the significant amount of element reshifting involved. For the brute force approach, the steps are as follows. We start by iterating through the array using a pointer, which we'll call I. Whenever we encounter a zero at position I, we shift all the elements to the right of I1 position to the right to make space for the duplicate zero. After that, we insert a duplicate zero at position I plus 1. Since we've added a new zero, we increment the pointer I to skip over the duplicate zero. This process continues until we reach the end of the array. However, this method has a time complexity of O(n squared), because every zero potentially requires shifting all remaining elements of the array. On the other hand, the space complexity is O(1), as no additional memory is utilized. To improve upon this inefficiency, we consider an optimized two-pass approach. The key intuition here is to avoid unnecessary shifts by first determining how many zeros need to be duplicated and then handling the placement of elements and zeros directly from the back of the array. The optimized two-pass approach is broken into two main steps. First, we calculate how many zeros need to be duplicated to fit within the original array length. To do this, we traverse the array while keeping track of the number of zeros and the effective array length after duplication. If the effective length exceeds the original size, we stop counting additional zeros. Next, in the second step, we process the array from the end, traversing it backward. By working from the back, we place elements directly into their correct positions without overwriting any values prematurely. If we encounter a zero during this backward traversal, we duplicate it by placing two zeros in the appropriate positions. This approach is efficient because it avoids excessive element shifting, which was a major drawback of the brute force method. Additionally, it ensures that the array is modified in place, adhering to the space constraint of O(1). It's important to handle edge cases, such as arrays with no zeros, arrays with all zeros, or zeros located at the end, to ensure the solution is robust. To implement the optimized two-pass approach, we rely on the input array itself, modifying it in place to save space. We also use pointer variables to track positions during the backward traversal. Let's walk through an example to see this in action. Given the input array 1, 0, 2, 3, 0, 4, 5, 0, we first count the zeros. The original array length is 8, and there are 3 zeros, making the effective length after duplication also 8, meaning no truncation is needed yet. Next, we perform the backward traversal. Starting from the end of the array, we place elements into their correct positions, duplicating zeros when encountered. This ensures that all operations are handled efficiently and that the final array satisfies the problem constraints. In the backward traversal phase, we start from the last element of the array. For example, if the last element is a 0, we place 2 zeros in the appropriate positions. Moving to the element before it, we simply place it in the next available position. This process continues as we work our way to the beginning of the array. For the example array 1, 0, 2, 3, 0, 4, 5, 0, this process results in the final output 1, 0, 0, 2, 3, 0, 0, 4. The time complexity of this approach is O(n), as we perform one pass to count zeros and another pass for the backward traversal. The space complexity remains O(1), since no additional memory is utilized. Key optimizations here include the use of backward traversal, which prevents overwriting issues, and the zero counting step, which eliminates unnecessary operations, making this method significantly more efficient than the brute force approach. This implementation starts by calculating the total number of zeros in the input array, which helps determine the shifting logic. We process the array from the end to the start. For each element, we compute its new position after accounting for the zeros to be duplicated. If the new position is within the array bounds, the element is placed there. For zeros, an additional duplication is performed by decrementing the zero count and handling its placement similarly. This ensures the array is updated in place while maintaining constant space complexity. The algorithm is efficient with a time complexity of O(n), due to the single traversal of the array. Here, we begin by importing the necessary Java utilities and defining our solution class, which contains the method duplicateZeros. This method takes an integer array as input and modifies it in place to duplicate each zero, shifting the remaining elements to the right. First, we calculate the length of the array and initialize a variable zeros to keep track of how many zeros are present. We then use a for loop to iterate through the array and count the zeros. For every zero encountered, the zeros counter is increment. Next, we start a second loop that traverses the array from the end towards the beginning. The goal here is to shift elements to their correct positions, including duplicating zeros where needed. For each element, we calculate its new position by considering the current index plus the remaining zeros. If this new position is within the bounds of the array, we copy the current element to its new position. This ensures that elements are shifted correctly without overwriting values prematurely. Now, when the current element is a 0, we decrement the zeros counter and prepare to duplicate it by placing another 0 in the shifted position, ensuring it's still within bounds. Finally, the code checks if the zero duplication is within the array's bounds and places the duplicated 0 appropriately. By continuing the loop in reverse order, we ensure that all elements are shifted and duplicated correctly without overwriting any data prematurely. This approach is efficient because it avoids creating a new array and works entirely in place, making it suitable for constrained memory environments. The result is a modified array where every 0 is duplicated, and the rest of the elements are shifted to the right. The method exits once the loop completes, and the input array has been transformed as required. Here, we begin with the first example where the input array is 1, 0, 2, 3, 0, 4, 5, 0. First, we initialize two key values, n, the length of the array which is 8, and zeros, the count of zeros in the array, which is 3. Moving to the iterations, starting with I equals 7, we calculate I plus zeros equals 10, which is out of bounds, so no action is taken. For I equals 6, I plus zeros becomes 9, which is also out of bounds, so still no action is needed. When I equals 5, I plus zeros equals 8, which is within bounds, so we copy the value at ARR 5 to ARR 8. This doesn't visibly change the array yet. At I equals 4, we encounter a 0. Here, we place a 0 at ARR 6 and decrement the zeros count to 2. The array now updates to 1, 0, 2, 3, 0, 4, 0, 0. Next, for I equals 3, we copy the value at ARR 3 to ARR 5. This updates the array to 1, 0, 2, 3, 0, 3, 0, 0. Then, for I equals 2, we copy ARR 2 to ARR 4, resulting in 1, 0, 2, 3, 2, 3, 0, 0. Now, at I equals 1, we find a 0 again. This time, we place a 0 at ARR 2 and reduce the zeros count to 1. The array now becomes 1, 0, 0, 3, 2, 3, 0, 0. Finally, for I equals 0, we copy ARR 0 to itself, leaving the array unchanged. The final output of this example is 1, 0, 0, 3, 2, 3, 0, 0. Now, let's consider the second example where the input array is 1, 2, 3, 4. Here, we initialize n to 4 and count the zeros in the array, which results in zeros equals 0 since there are no zeros at all. During the iterations, because there are no zeros to process, no modifications are made to the array. For every iteration, starting from I equals 3 down to I equals 0, each value in the array remains in its original position. Thus, the output of this example is simply 1, 2, 3, 4. In the third example, we have an input array of 0, 0, 0, 0, where all elements are zeros. First, we initialize n to 4 and count the zeros, which results in zeros equals 4. Now, during the iterations, starting with I equals 3, we find that ARR 3 is 0. We attempt to place a 0 at ARR 6, which is out of bounds, and decrement the zeros count to 3. At I equals 2, ARR 2 is also 0. This time, we place a 0 at ARR 4 and decrement zeros to 2, but the array remains 0, 0, 0, 0, since it's already filled with zeros. Similarly, for I equals 1, we place a 0 at ARR 2 and decrement zeros to 1. Again, the array visually remains the same. Finally, for I equals 0, we process the first element, which is 0. Here, we place a 0 at ARR 0 and reduce the zeros count to 0. At this point, all the zeros have been processed, and the array remains 0, 0, 0, 0. This concludes the example with all zeros, and the output is 0, 0, 0, 0. The time complexity of this solution can be understood by breaking it into two main steps. First, we count the number of zeros in the array using the ARR count 0 operation. This requires scanning the entire array once, so it takes n time, where n is the length of the array. Second, we process the array in a backward pass using a loop that iterates from the last index to the first. Each iteration involves constant time checks and assignments, meaning the loop itself contributes n time. When we combine these steps, the total time complexity is the sum of the time for counting zeros and the time for the backward traversal, which is n plus n, simplified to n. This linear time complexity ensures the algorithm scales efficiently with the size of the input array. The space complexity of this solution is minimal because it modifies the input array directly without creating any additional data structures. Specifically, the solution operates in place on the array ARR and does not require extra space for copying or storing intermediate results. Additionally, the only extra variables used are zeros, which stores the count of zeros, and the loop counter I. Both of these are simple integers and require constant space, or O1. Therefore, the overall space complexity of the solution is O1, making it highly space efficient. Now, let's analyze the best, average, and worst-case scenarios. In the best case, where there are no zeros in the array, the loop still executes, but no extra assignments are needed to duplicate zeros. The time complexity remains O(n). In the worst case, where every element in the array is a zero, each zero requires duplication, which results in the maximum number of assignments. However, even in this case, the number of iterations and assignments remains proportional to n, so the time complexity is still O(n). For the average case, with a typical mix of zeros and non-zeros, the algorithm still processes the array in O(n) time. Compared to a naive approach, which might involve creating a new array and explicitly inserting zeros, our optimized solution avoids the O(n) space overhead of the new array. While both approaches maintain a time complexity of O(n), the optimized solution achieves this in place, reducing the space complexity to O(1). We can further justify the big O notation mathematically. The dominant contributor to the time complexity is the single traversal of the array. While duplicating zeros involves additional assignments, these are handled within the same traversal and do not require extra passes through the array. Since the algorithm performs a constant amount of work per element, the total work is proportional to the size of the input, making the time complexity linear, or O(n). Additionally, the absence of recursion or supplementary data structures ensures that the space complexity remains constant at O(1). To summarize, the solution achieves a time complexity of O(n), driven by the single traversal, and a space complexity of O(1), thanks to in-place modifications. This makes the solution optimal compared to a brute force approach, which requires extra space while achieving the same time complexity. When working on the duplicate zeros problem, there are some common mistakes that you should be aware of. First, not handling shifts properly can lead to overwriting data. This often happens when duplicating a zero and shifting elements to the right, especially if you're iterating forward through the array. The order of operations can disrupt the position of subsequent elements. To avoid this, a good practice is to use reverse iteration or a two-pass approach, which ensures data integrity. Another mistake is ignoring the fixed array size. Since you cannot expand the array dynamically, trying to access indices beyond its bounds can lead to errors. It's important to manage indices carefully and perform all operations in place. Lastly, overcomplicating the solution is a common pitfall. Using additional data structures like auxiliary arrays might seem easier at first, but it increases space complexity unnecessarily. Instead, focus on in-place transformations to meet the problem's requirements efficiently. Another issue you might encounter is off-by-one errors. These occur when you miscalculate the range of iteration, which can lead to skipping elements or duplicating zeros incorrectly. This is particularly tricky when you're shifting elements or performing reverse iteration. To prevent this, make sure to track your indices carefully and account for overlapping operations. Additionally, overlooking edge cases can result in incomplete solutions. For example, consider arrays without any zeros, arrays full of zeros, or arrays where zeros occur at the boundaries. Each of these scenarios presents a unique challenge, so it's crucial to test your solution on a variety of inputs to ensure it handles all edge cases correctly. In interviews, there are a few key insights to keep in mind for problems like this. In-place operations are often a core requirement for array manipulation problems, so minimizing the number of passes and avoiding extra space usage is critical. A highly effective strategy here is the two-pass approach. The first pass determines how many zeros need to be duplicated while respecting array boundaries. In the second pass, you work backward to duplicate zeros, which prevents overwriting elements. Recognizing patterns is also important, as this problem falls under the category of array transformations with constraints. Similar problems include shifting elements, merging sorted arrays, and maintaining sliding windows. When communicating your solution, be sure to explain how you handle edge cases and why a particular iteration order, like reverse traversal, is optimal. Finally, practicing related problems such as remove duplicates from sorted array or move zeros can help you better understand these patterns. There are alternative approaches to solving this problem, each with its own trade-offs. The brute force approach involves iterating through the array and, whenever a zero is encountered, shifting all subsequent elements to the right before duplicating the zero in place. While this method is simple to implement, its time complexity is O(n) squared due to repeated shifting, making it inefficient for larger inputs. On the other hand, the two-pass approach is much more efficient. The first pass calculates the number of zeros that need to be duplicated while ensuring that array boundaries are respected. The second pass then duplicates the zeros in reverse order, which prevents overwriting existing elements. This method has a time complexity of O(n) and operates in place, but it does require careful management of indices to avoid errors. Lastly, the auxiliary array approach provides another way to solve the problem. In this method, you create a new array and copy elements from the original array, duplicating zeros as needed. Once completed, you replace the original array with the new one. This approach is straightforward and avoids the complexities of in-place transformations. However, it has a time complexity of O(n) and a space complexity of O(n), since it uses additional memory for the new array. While this method is easy to implement, it doesn't meet the constraints of problems that require in-place solutions, making it less suitable for certain scenarios where minimizing space usage is critical. Great job! We've completed the problem duplicate zeros and explored how to solve it step by step. Remember, mastering in-place transformations is a valuable skill for technical interviews. Thanks for watching, and don't forget to like and subscribe for more problem-solving tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!